Hello, my lovely students. It's been a while. This video has been brought to you by a very generous student who decided to sponsor one. If you would like to commission a video, just email me at naughtymathprofessor@gmail.com and we can work something out. I hope you enjoy this in the meantime. Today, I thought I would talk about more. How do mathematicians define more? How do we define more? And how can we even understand this concept? It seems pretty basic. When you're a child, you can understand that if you have one cookie and someone else has 2 cookies, that they have more. The way that we understand that is by creating something that's called a bijective correspondence. We can say, if I put my cookie here next to your cookie, if we pair them off, you have some cookies left over. We can't pair them off. There's no way that we can match up our cookies. We can't pair them up. Special guest spot by a kitty for you there. Unfortunately, the only pussy you will see in this video. If 2 collections of things can be paired off like that, then we say that they're exactly the same size. If they can't, then we have to do some funky work with adding or subtracting them and seeing what kind of answer we get. It gets strangely complicated to even conceive of what more means. So let's look at it this way. Let's look at a pairing. Let's say that I am with a man and he is enjoying one of my lovely breasts and his tongue is playing with my nipple. I have 1 tongue and 2 nipples. There's a nipple left over, so there are more nipples than tongues. If I was with 2 men and they were each enjoying one of my breasts, I would have a bijective correspondence between tongues and nipples. If I invited a 3rd man, I would need to find some more nipples to satisfy everyone. So there's a nice little example that you can keep in mind for bijective correspondence. 1 tongue, 1 nipple, paired up. Let's look at some examples of mathematical sets. So if I were to take the letters of the alphabet, from A to Z, and the numbers from 1 to 26, I could come up with a very, very clear, very, very obvious bijective correspondence. A goes to 1, Z goes to 26, B goes to 2, C goes to 3. Nothing too exciting here. Those are finite sets. They each have size 26. So we can pair them up really nicely. It's clear that neither of them has more than the other. Where the idea of more gets really complicated and really hard to understand is when we're talking about infinite sets. When we're talking about a collection of things that really has no end. Every breast that will ever exist on planet Earth. Every tongue that would ever want to lick one. Which of those is more? I mean, I guess it's going to turn into some sort of debate about whether there will be more female breasts or tongues out there that enjoy female breasts. It would get really complicated, it would get really tricky, and when it comes down to it, they're both infinite, and they're both what we call countably infinite. we could line up every breast. We could say, here are the first two breasts grown on Eve. And we could move forward from there, and we could line up every breast, and we could put them in chronological order. We could do the same thing for tongues. We could put them in chronological order. We could line them up. The line would never end, but we could line them up. And this is true of the counting numbers. We could say 0, and 1, 2, 3, 4, 5, 6, and so on. We could line them up. We could also do this for the integers, the positive and negative counting numbers. We could do something like 0, and then 1, and then negative 1, 2, and then negative 2. As long as when I put those 3 dots there, you can predict what I'm going to do next, that means that I've given you a countable set. I've listed numbers in a way that you can imagine listing all of them forever. Even though forever is very hard to imagine, you can still get what I'm going at. You can see that I could list them as long as you needed to. For any amount of time, I could list them that long. For any number, I could list until I was going to get there. Alright. This gets a little tricky when we think about fractions. Here I'm just listing them in order of size, growing. Here I'm doing this kind of bouncing thing, but I'm still sort of listing them in order of magnitude, in order of absolute value. If I were to list all of the fractions, I could be like, well, let's see, we've got 0, we've got 1/2, we've got 3/4. Oops, I forgot 1/4. I better squeeze that in there. Oh, right, but I forgot an 1/8. That's got to come before 1/4, right? So I have to squeeze that in there. And before we know it, time has ended. We've spent forever just trying to list the numbers here. So that's a problem. So it seems like we might want to say that there are more fractions than there are whole numbers, because when I try and list them like this, it just doesn't work. But that's a problem. Mathematicians can't say that I tried and I failed, therefore it's impossible. We need to try again. Alright, we could try forever, and we could still fail, but that still doesn't mean it's impossible. We have to be sure that it can't be done. And in fact, with fractions, we can do it. We have a very cute counting method for this. Let's see, we have the numbers. 1/1, 1/2, 1/3, 1/4, and then for an extra we'll do 2/1, 2/2, 2/3, 2/4. I think you can see where I'm going here. In every direction. I could make a grid that has every fraction on it. Now, the astute observer who's really paying attention to my hands will notice that I have 1/1 here and 2/2 here. I have 1/2 and 2/4. Those are equivalent fractions. Not only do I have all the fractions, but I have some duplicates. Not a problem. Don't worry about it. Not going to matter to us because we're going to make a list. We're going to say, okay, we start with 1/1. Then I'm going to do 1/2, 2/1. Then I'm going to do 2/2. Oh, I need to make this picture a little bigger, don't I? Let's see, then I could do 3/1. 2/2, 1/3, then I could do 1/4, 2/3, 3/2, 4/1, It's certainly not as obvious as listening to counting numbers. I'm not going to say that this is just like the natural numbers, just like the integers, but it is a way of writing them in a list where you, the casual observer, can tell what's going to happen next. If I give you the beginning of this pattern, you can say, okay, well, next it's going to go down here to 5 over 1. Even though I haven't written it there, you could fill in this table by yourself, and you could write a million entries in it. You can write infinity, but you could write an awful lot. So it turns out that there is a correspondence between the natural numbers and the fractions, which is wild, because it seems obvious that there are more fractions. Every natural number is a fraction, and not every fraction is a natural number. How can it possibly be that there aren't more fractions? And this just comes down to the weirdness of infinity, the weirdness of everything. When you get everything, it gets really big. So big that it's kind of hard to tell, like, who cares an extra fraction here? It's basically the same set. Alright, so we've got this one bijection. I could say, like, here's 1, here's 2, here's 3, here's 4, here's 5, 6. So I could order the numbers, I could line them up with all of the counting numbers. Is there anything that's bigger than that? Is there anything that's bigger than infinity? It's a weird question, because infinity, right? So, I'm going to tell you that there is, and then we'll see why. First of all, we know the fractions aren't big enough, so we need to add some things. So I want you to think of numbers that aren't fractions. Think of pi, and square root of 2, and all those really funky, naughty numbers that can't be written as a fraction. Those are all real numbers. Some of them are what's called transcendentals, and some numbers are just wild, but they still fall into the real numbers. The real numbers are anything that can be written in an expansion, a decimal expansion, even if it has to be infinite. Now, some infinite decimal expansions, such as infinite threes, those are actually expressible as fractions. But some decimal expansions, such as, now we really shouldn't be doing a dot, dot, dot here, because you have no idea what comes next unless you've memorized pi more than 6 digits, which, yeah. This is pi, can't be written as a fraction, never going to repeat. In fact, once a decimal starts repeating, it can definitely be written as a fraction. If you want to know why, hit me up. So, we have some decimals that are not fractions, some decimals that are fractions, and I'm going to tell you that if we look at all the real numbers, all the decimals in the world, it's more than the number of fractions. In fact, I'm going to make a set that's going to seem so tiny, it's going to be absurd that we find out that it's actually more than the fractions. Let's say that we've got a set of all numbers where x is between 0 and 1, and x's decimal expansion only contains zeros and ones. And yes, I know grammatically those apostrophes are against the rules, but mathematicians do them. We're rebels. What can I say? This set is going to be bigger than the fractions. Even though it's this tiny little thing, it's just the stuff between 0 and 1, and it's not even all the stuff between 0 and 1. 0.3 isn't in this set. Alright? Nuts. So, how can we be sure of that? As I said, we can't just try and say, oops, I failed. I guess it's not possible. We have to be sure it's impossible. That's a lot to ask. To be absolutely sure that something's impossible, that's proving a negative, which a lot of people like to say is impossible. Totally possible. So we're going to prove a negative. We're going to prove that this is impossible. We're going to use what's called the contradiction method. We're going to assume that it's possible, and then show how, if it was possible, dogs are marrying cats, the world explodes. If it's possible that this set is the same size as the natural numbers, then anything could happen. I should be able to think of something insane a lot quicker than that. You can climb through this computer screen and take me now. So, let's pretend. Let's go into a world of make-believe. Let's say that these two sets are, in fact, the same size. That means that I can list everything in this set. I can just say, well, this is the one that goes with 1, this is the one that goes with 2, I can make a list of them. So let's say I've got a list of decimals. It doesn't really matter what these are. We've got a list of decimals. They just have zeros and ones. They're between 0 and 1, so they don't have a leading number here. And we're going to say, let's say that this is a list that can be created. It's possible to list every single number in the set. So just write them out. Here's the first, here's the second, here's the third. I'm going to do a funky little trick here. I'm going to take a new number, and I'm going to base it on the pieces of this. So I've got my list. I'm going to take the first out of the first number, the second out of the second number, third out of the third number, and so on. And I'm going to take the opposite. So here I've got a 0. My new number is going to have a 1. Here I've got a 0. My new number is going to have a 1. Here I've got a 1, my new number's going to have a 0. This number isn't going to be anywhere on the list. I've made sure that somewhere in its decimal expansion, it breaks with every single one of the numbers on this list, because I can just go on forever and just make sure that it's wrong in one place. It can't be the first number because its first digit doesn't match. It can't be the second number because its second digit doesn't match. It can't be the 500th number because its 500th digit doesn't match. So I've guaranteed that this number cannot be on this list. And why is that a problem? Because in our make-believe little world that we're living in right now, everything's on the list. We just found something that isn't on a list of everything. We call that a contradiction. We say something went wrong, and therefore our initial assumption was incorrect. Right? It's important that we only made one assumption. We didn't go and make up a complete fantasy world. We just said, okay, it's just like everything else except these numbers are countable. Alright, now just like the fractions, we had extra numbers in there that we didn't really need. Just meant we were looking at a bigger set, and the bigger set was the right size. This is a smaller set that is already bigger than the fractions. It's already what we call uncountable, because we can't list everything. And so, we're done. All of the real numbers are definitely going to include this set. They include something uncountable, they have to be at least uncountable. You might ask, is there something bigger than uncountable? And it turns out there are so many infinities. When we say infinity, we're being a little bit silly. There's way more than one infinity. Infinite numbers of infinities, in fact. And maybe we'll explore that another time. Until then, I have been your naughty professor, at your service. I hope you enjoyed this video, and I will see you next time.